Hello, this is Paul from Fossil Tech. In this video, let's prove Theorem 5.2.2, linear independence of eigenvector. We have two results, and the first result says different or distinct eigenvalue get a different or distinct eigenvector. The eigenvector are linearly independent. The B says if A has n by n, is n by n matrix. If A has n distinct eigenvalue, then A is diagonalizable. B first. Okay, let's look at it. B is obvious. Okay, because and A says eigenvector corresponding to distinct eigenvector, they are linearly independent. So, and from here to here is obvious from A to B. Because if A has n distinct, that means A has n linearly independent eigenvector, right? And then by the previous theorem, Theorem 5.2.1, okay, if A has n linearly independent eigenvector, and then A is diagonalizable. So I leave this B just for you. We'll look at A. First, let me just set up in this. Okay, so we already have lambda I. So we say Vi is corresponding to lambda I start from 1 to goes on to k. And this, remember, lambda I is distinct and different. So we need to find all the eigenvectors are linearly independent. So we can do in this way. Okay, we just explore first one by one. The first step, look at just one vector. Okay, so for example, it's just a V1. And I know this should be linearly independent. This is true. This is linearly independent because I know eigenvector is not a zero vector, right? Okay, therefore linearly independent. Good. And if we look at any vector, one eigenvector, they should be linearly independent. If I look at 2, now, for example, I'm looking at V1 and V2. Is V1, V2 linearly independent? Okay, think about this. What if they are linearly dependent? I get something wrong. See, easily. Otherwise, linearly dependent. Let me simply say V2 is a linear combination of V1, which is a scalar multiple. We can get something wrong from here. How? I left multiply. See, imagine. And here I left multiply A. And on the right side, I also left multiply by A. And therefore, we should get something, which is A times V2. It is true, right? By the definition of eigenvector and eigenvalue. So I should find A times V2 is lambda 2 times V2, right? Okay, so that's the definition of an eigenvalue and eigenvector. Is this something wrong? No, I don't know. I have to plug. V2 is a scalar multiple, okay, to here. See, imagine. What is V2? Okay, V2 is this one. So I can just plug this in, which is K times V1. Oh, this time I definitely know something. So the left is a scalar multiple of V1, the right also the same. Therefore, the coefficient should be equal to each other, coefficient, right? So the coefficient lambda 2 is different from lambda 1, remember, distinct. So therefore, this k should be 0. Otherwise, the left does not equal the right. Make sense? Okay, so now I should find k is 0. Otherwise, wrong. And if k is 0, okay, by the beginning V2, I get it. V2 is k times V1. Okay, 0 times V1. Therefore, is 0 vector. this is definitely wrong, right? Conflict. Because eigenvector never be a zero vector. Okay, so I should find it. This is true, right? Okay. So this means any two eigenvector they put it together should be linearly independent. Let's do one more. So how about the 3? For 3 is very similar. So you can look at let's say V1, V2, and V3. Is this linearly independent? I say yes, but we need to explore why. So follow the same idea we did in the second step, 2 vectors. Okay, see, if these 3 are not linearly independent, therefore linearly dependent one should be a linear combination of the another 2. So therefore, we can get this. Let's say V3 is a linear combination of V1, V2. Okay, so now start from here it's the same. Okay, so I left multiply A, left multiply A, left multiply A. See, we should have this now, right? And then by the definition, so we can change it to change A to the eigenvalue. Okay, so now for V3, so keep in mind that so we say this a linear combination. Let me put a V3 here. So V3 should be K1, V1 plus K2 and the V2. So start from this sentence. We have 2 vectors V1 and V2, right? And then we can combine like terms. See, what do we get? I easily get the coefficient for V1. I put the left to the right side. So should be K1 lambda 1, K1 lambda 3. Therefore, it's this. Okay. See, I do find the coefficient in this form. Remember, this lambda should be distinct, so this is not a 0. However, we know these 2, okay, from the second step, these 2 are linearly independent, right? See, from the second step, if you check, 2 eigenvalues should be linearly independent. These 2 linearly independent, therefore the coefficient should be 0, right? But this is not a 0. Therefore, I should get this. This is not a 0, definitely. This is not a 0. And therefore, I get a K1 should be 0, right? And then again, this is not a 0. So this K2 should be 0. Therefore, I get this result. K1, K2 is 0. Means what? Means back to V3 should be 0 vector. Okay. Yeah. Is this possible? Of course not. Because V3 is eigenvector. Okay, it is not 0. So therefore, conflict. We back to this should be not linearly independent, not linearly dependent. Therefore, we prove the results. That's 3. And the same are 4, 5, 6. Or you can use mathematical induction. Okay, so you can leave this for you. So you can use. Okay, I just leave this for you. That's all. Thank you.